you smooth the data, it's kind of neat. In one of my programs, I use a Gaussian filter, but the moving averages works just as well, many instances. So the top one is a typical noisy curve that I generated, an artificial curve, and then successively smoothed as you move downwards. And so it looks nicer, but there's still bulges and things, so there's still noise there. I believe that this helps Quee van Woerden bisector sliding integrations, makes them work a little better, but curve fitting doesn't need smoothing because you don't generate any more information by smoothing. Okay, it's just an artificial technique to try to make some methods work better. Very shallow eclipses. Okay, so this is one of the really obnoxious, horrible data sets which you get on a totally rotten night. You can fit this with the quadratic, and it doesn't look that bad, to me, in spite of some of those horrible points at the bottom there. My point is that you could use data like this as long as you put the error estimates big enough. And in some of the curves I'll show you later on, you'd really like to have a data point, however inaccurate, because it's better than nothing. If it helps you keep track of the cycles, then that's of use. So just make sure your error estimates are big enough. Flat bottom light curves. For Quee and sliding integrations, it might make sense to replace the flat bottom part with a straight line. For bisectors, it's not used anyway, so it doesn't matter. For curve fitting, just exclude the data from the flat region. This is an actual star TZ Butai that I did in February. Having said all that, the different methods there are fairly comparable in the answers they got. So much of what I've been saying about errors have been worst cases. And a lot of the time, it's not that bad. Okay, so in fairness. Off-center data. Bob asked about this one. What do you do if you have more data on one side than the other? In this case, yes, I could have kept going with VY Ursa Majoris, but I figured I had enough, so I quit and went over to another star. The data, when it's in the shoulders there, isn't varying very rapidly, and so it's not particularly valuable in determining the time of minimum. The best times are when the curve's the steepest, because then you get the most accurate constraints on the time of minimum. So in this instance, I did Fourier fitting with, on the right there you can see a column involving all the data, and then the column just to the left is with the regions fit by the blue line. And you can see that the difference is not much. So curve fitting works with all of your data, and so the Fourier fit might make sense to use all your data some of the time. There's a bit of a problem here that I'll mention in a minute. But Fourier fits all the data. Quee can't handle the data on the left. None of the other methods can. Asymmetric light curves. This is a big problem. This is kind of a mild case here. As a matter of fact, some of the data looks as if it's just an error. Sorry, I apologize. I meant to put in some really serious cases that are much worse than this. Sometimes your light curve is asymmetric, and the reason for that is maybe the maxima are different heights, and the reason for that is called the O'Connell effect, and it's usually ascribed to star spots or bright regions that you see on one part of the cycle and not others. And so the solution for asymmetric light curves is just to use the bottom part that actually is symmetric. That would be the solution. So that's what I'll have to say, but it is a bit of a problem. And if you get if I can get back to a flat light curve here, if you get to a flat bottom light curve and that portion at the bottom isn't flat, like maybe it's got a slope to it, then that should tell you that you've got a bit of a problem there. So either there's differential extinction or something going on. I can't be any more helpful than that because I haven't been very successful in dealing with it. But it probably deserves more attention than I get. If you have any kind of a slope to that, if you had differential extinction and there's a slight error from one side to the other, that has a huge effect on your time of minimum. I mean, it's non-trivial, it's huge. And I'll say more about that in a moment. Okay, rejecting data. I added this one. And then I started looking around to the internet for what to do about bad data points. And one criterion, I meant to look this up and then I didn't get around to it. I think it's the Cauchy criterion where things that are more than 3 standard deviations away from your fitted curve can be rejected. That's the criteria that some people use. And it sounds reasonable, but there can be problems. So in looking around, I found this piece by Dr. Judah Levine at the University of Colorado. And I put this PDF, it should be on the Dropbox. It's very instructive. It's quite interesting. He derives a whole bunch of stuff, including why we use the squares. But he's most emphatic about this. Just don't reject data. Just don't do it, he says. Unless you can justify it from some other reason. So don't reject points just because you don't like them. Mentioned in his paper, it's rather pithy. Be very careful, you're treading in the footsteps of a long line of practitioners of pathological science. So there are a whole bunch of bad scientists that have rejected data and come to all sorts of wrong conclusions because of that. And he mentions in there an example from CERN in Europe, well, the American astronomers, of course, too. They actually rejected some data that was real, and they came to a wrong conclusion. And these guys are the pros. These guys should know better. And they did that, and they came to just a very bad conclusion. So I recommend reading about that. It's quite interesting. So it gives you pause about rejecting data. I reject data, and I'll tell you why in a minute. One of the things I do in my plotting of data is I plot the raw magnitudes of a star. That's just from the basic formula, minus 2.5 times the logarithm of the number of counts divided by the exposure time, of course. And that's very interesting because it shows what your sky is doing. And so you can see from the upper right-hand plot there, the sky isn't too bad for me that night, back in April. But then towards the end, after JD 0.86, it gets really awful. And that's reflected in the light curve below it. You can see it's really awful there. And so that would be good and sufficient reason to reject that data. Oddly enough, if you plot the check minus the comparison star, which we all should be doing, it's very flat there. So I have no explanation for that, other than that perhaps the two stars were close together and not too affected by the clouds. Rejecting data. Here's another example. One of the biggest reasons for bad data is just clouds. And this particular light curve, which I got in May, I have a couple of bad points there. I have absolutely zero problem with throwing those points out. In principle, there could be something else going on then, but personally I doubt it. Maybe there's an exoplanet there. Ooh. I guess I'm going to have to run that risk of rejecting some meaningful data there. But this is so common that, you know, if we look at what the three different methods got, Cui seemed to be fairly seriously affected by it, whereas Fourier didn't, implying that Fourier was better. But then I thought, well, maybe Fourier looks good just because these points are near the center. So I generated some artificial bad data points off-center, and Fourier had problems there too. They all had problems, so that seems to be clear there. I really don't have a lot of problem throwing out data points that look like that. Then when you come to O minus C curves, I mean, look at the stuff on the left. It's horrible. And that's in IBVS. And that's quoted to 4 decimals. Presumably it's CCD. I don't know where it's coming from. Usually when I'm plotting these things and I see that sort of nonsense, I go back and check that I get the right star. I mean, that mistakes happen, and that could be for a different star, but it wasn't. I checked. It's the same star. So what the heck's going on here? I have no idea. So all of the data points on the left I reject. Then we come to a point near the middle of the plot. What's going on there? We don't know. It's somebody else's data. What are you going to do? I mean, I think most of the time you just have to just chuck it out. That's so common in O minus C analysis. But then I got to thinking, look at the 3 points just before it. They seem to almost fit in a straight line. See these 3 points here, 4 points here, seem to plot in a straight line. So could it be that I have the cycle count for the last point, which is mine, by the way? So I tried that, and then let me see. What's going on here? Yeah, so that point looks good, and then one of mine looks bad. I think that's what I'm trying to say here. It looks like this point now is bad. So, I don't know. It's interesting. It's charming. So the answer is often just take more data. You'll find out. Miscellaneous problems. This happened this year. I set my telescope going and went to bed, as I often do. And I don't really have to worry about bad weather because I have a cowling that I put over my CCD camera, so even if it rains, the camera's protected. The mirror will get wet, but then, you know, I just take more flats or clean the mirror or something. So I don't have to worry about when I leave my telescope going overnight. My wife puts the telescope away in the morning for me. It's kind of neat. But anyway, as is usual, I set the telescope going on a star and I went to bed. And what happened was that, I don't know exactly what happened, but the guiding software jumped to the next guide star. And so everything was displaced. Well, it's okay, so you just reduce that set of data separately from the stuff before. And I get this horrible jog, which, you know, is kind of worrisome. If you look at this curve on the left here, it doesn't quite fit. It doesn't look that good. And then, of course, if you look at the C minus K graph, then you see a definite step. Okay, so it's about 0.01 magnitudes. And so what I said was, okay, why don't I just add 0.01 to everything on the right? Okay, and now it fits better. It looks nicer. And the C minus K fits better. Is this legit? I have no idea. It looks nice. But see, here's the deal. If you look at, I don't seem to have it plotted here. If you look at the times of minima, oh, right, there we go. Where have we got it? Oh, yeah. The times of minima that I calculate from the two different methods are shifted by 0007 days. Okay, so that's about 8 times, that's about a minute. Okay, that's about a minute out. So what do? So I'm quoting the better result, but then I'm putting an error estimate of that. And then I'm not sure I didn't double that as well. So I think you could use dodgy data as long as you put the error estimate big enough. You know, be pessimistic. Pick something and then double it. Having said all that, there's my point over there with the error bar. It's quite a reasonable point. Why is there so much scatter in the data points from the other guys? I have no idea. It may be that there's, most likely there's some physical process going in the star which is doing that. So that's why we have that. Miscellaneous problems. For this reason, I never attempt to combine data from each side of a meridian flip. It's no longer an issue with me because I don't have a western sky anymore, so I just work in the eastern sky only. But I've tried before to combine data from both halves, and it's never had a good result. In theory, you should be able to take flats on each side, and my friend and colleague in Melbourne says you use a rotator, so then you turn the camera around, so it's the upside down, and do flats on both sides, and he claims that he can do that. Maybe you can. I just don't recommend it. There are too many uncertainties there, and you just only have to be off a little bit in magnitude, and you throw off the time of minimum a lot. So I just don't like it. And with our remote telescope in Arizona, it's a fork mount, so we never have to worry about that. However, this raises another issue. Are you sure that the images that you take over in this part of the sky are comparable to the images you take over there? If you've got mirror flop, it might be a bit of a problem. I think my telescope has a mirror flop, and I should attend to that. So I'm probably going to have a down period this summer, and I'll do some real maintenance on it. That's probably a good idea. So anyway, it's good to think about these things. Here's another cute little problem that arose. The data here for this star, obviously it eclipsed sooner than I expected, and that's why I'm glad I started early. We've got some data there, and then 4 points that are above my fitted curve and 2 below, and what's going on there? Well, it turns out that the Fourier fit algorithm works very nicely for this kind of data. We're using information on the right from the shape of the light curve to generate the fit, and then the time minimum is an independent parameter, which is the thing we're solving for. So Queen Van Woerden and sliding didn't work very well compared to the other guys. Okay, so that's what we have. Again, the O minus C curve for this is interesting. We don't quite know why we have that kind of variation. I don't know. But anyway, for my money, Fourier fit is the nicest method to use here. What do we do with this? I have no idea. The software there at the bottom is what I call Tomcat, which is an acronym for Time of Minimum, Calculate and Test. So it's a modified Fourier transform. I square something up along the way, I think, to accentuate differences. And so it generates the plot you see at the bottom there. And what we need is values near 0. And so quite clearly there's a spike there. And that's where the best period is. So I tested all of these data to find the optimum period, and that's it. So Tomcat works quite well for long period stars, more than a day in period. You can often nail the period with that, but it doesn't work well for short period stars because there are a lot of aliases that come in. And so sometimes you get a plot like that with lots of spikes on it, and so you can't tell what the proper minimum is. And the best way to determine the correct period is to do a full light curve, and then you know for sure. Or at least get some times of minimum very close together, and you can exclude all of the aliases. So I use this quite a bit. And you can also have a copy of that if you want. Here's some software and computer and equipment issues. We've all done this. Can't find the star. And can be very, very frustrating. It could be that your pointing model is off, that needs to sync. My pier is ridiculous. I built it before I knew any better, but even if I did, I would have had trouble getting a contractor to dig the hole that I wanted. I met an astronomer once that had 3 yards of concrete in his pier. 3 yards of concrete. That's a lot of concrete. He says, well, concrete's cheap. The rest of my equipment is not. So he's got a pier that'll, last almost anything. I drool when I think about that because my pier does shift a little bit with the seasons as the ground freezes, but it sort of works. So my pointing model isn't always that accurate, but I can usually put the star on the chip, so it's not really that big a problem. But if you can't find your star, probably the best thing to do is to go to a nearby bright star, and then you can put that on the chip and sync on that, and then you'll probably be able to find your star. There's another really slick method. The SkyX has a plate solve. You guys know about that? You can take an image. I have no idea how it works, but you can input the image and it tells you where it is in the sky. It's ridiculous how well it works. It doesn't always work though, but it's pretty amazing when it does. There are other implementations of plate solving. Does anybody know of them? Anybody use it? Go ahead.
I use astronomical.net on it to design things, and I'll use Pinpoint to for all my image shots.
Pinpoint. Yeah. That sounds good. Okay. Okay, I'll pay a visit. Lost guide star, that's happened. Obviously stop the auto guider, retake a frame, move the telescope around, get going again. Glass plate frosts over. If your desiccant needs recharging, then if you try to cool it to -30 or something, then the frost forms and so you have to kill the cooling and let it warm up and replace the desiccant. If you have a spare desiccant handy, that's very helpful. Anyway, the last one is a nasty one. If all of a sudden it's happened to me, I don't know what's happened to you. You can't connect to your camera all of a sudden. It just says no communication or whatever message it gives you. Blah. What do? Well, usually I just either reboot the software or just reboot the computer. So if you've installed your camera correctly at the beginning, and with the SBIG cameras, there's a definite procedure. They tell you exactly what to do to install the USB drivers. If you've got the USB drivers in, then it will work again. So usually what you need to do is reboot your computer. Mistakes. We've all done it. Here's a list, but it's not exhaustive. You're sitting inside doing something, watching a movie or reducing data or something, and it's clear outside and you haven't noticed. I hate that. So check the sky often. Set the date wrong in your predictive software and then you get something wrong. I used to get in trouble with the time zone change, so I've put that in my software now, which works for North America, if you don't live in Saskatchewan or Arizona, etc. I always recommend putting down the start time of one of your exposures, because then you have something to go back and check. It's just good procedure, I think. Wrong star. You've all done this. You just have to be careful. Do you guys know about Aladdin? It's kind of neat software. You just type in the name of a star and it gives you an image which you can zoom in or out. You can get that in Sinbad, but Aladdin is nicer. Forgetting to run a series, you take exposure and you forget to tell it to run a series, and it's just sitting there doing nothing while you're gazing at another computer doing something else, and you, oh God, it's not doing it. I set my telescope going and then go to bed, so sometimes if you forget to set it going and go to bed, then you're going to end up with nothing. If you do something else and the screensaver is running on your observatory monitor, then you don't notice if it's lost the guide star, and so you can wake up half an hour later, oh no, it's getting garbage. Letting the images become overexposed. You don't want to exceed half the full well depth, because then you get into the nonlinear region and you've got crap. So generally you have to babysit your telescope. You have to keep an eye on it once in a while. The baby monitor is not enough. You need to just be reducing files early, be on top of the situation, and make sure that nothing's going to go wrong. So more on the O-C plots. I'm trying to convince you that these things are cool things, and there are a lot of things that come in here. So 44I Boo is a very bright visual binary, and it's also the brightest eclipsing binary in the sky, I believe. So the top is the visual binary orbit, as you can see, is it's around 100 years, a little over 100 years. And the bottom is an O-C plot for the eclipsing pair, which is the, so it's A-BC, okay, in the nomenclature. A is the brightest star in the center, and BC are the orbiting pair that are in turn orbiting around the central star. So anyway, the BC pair is an overcontact binary, the closest to the Earth, and below you see a plot, an O-C plot. So you look at that and you say, oh well, it's a nice quadratic, it's increasing period, and blah-de-blah-de-blah. It's not quite a parabola, so you can actually plot some other function to it. Now Hill et al. In 1989 complained that everybody else was neglecting the fact that there's something called the light time effect going on. So if I can use my hands here, we've got the central star with the other one pair going around it like this. Okay? Well, now when the eclipsing pair is on the other side of the orbit, it's going to take light longer to reach you than when they're on this side. Okay? So that's the light time effect, and you have to take that into account. And this guy, John Irwin, from Indiana University, back in 1952, published all the equations that we can use. Okay, if you're good at mathematics, you could derive these. I haven't actually gotten around to doing that, but it's not that difficult. It's just using the orbital equations. So what we have is the eclipse times may then be predicted by HJD 0, which is your starting time, plus the period times the number of cycles, that's a linear term, plus a quadratic term, plus another term, tau. Tau is the time delay or the time advance, depending on where your orbiting pair is in the larger orbit. We call it the light component. Right at the bottom you see kind of a complicated looking equation. E is the eccentricity, that should be a nu, that's an angle in the orbit, and so is omega, and so that allows you to calculate the correction. Okay, so this is the paper published by this chap, And I've been able to put his equations into an Excel worksheet. You can do almost anything in Excel. So powerful. So these are the parameters that I can change. So I'll just try and explain them just a little bit. The top one there is the constant for the parabola. This is the slope, and this is the quadratic coefficient. Okay, A is the amplitude of the motion as it's going around the larger star. So that involves the size of its orbit plus the inclination. E is the eccentricity of the larger orbit. Okay, equals 0 is a circle, and E equals 1 would be a straight line. So eccentricity is somewhere in between. P3 is the orbital period of the larger orbit, and this particular system here is 225 years for the larger orbit. I think I got it wrong earlier. Omega is one of the constants. It's called the argument of the periastron. Okay, T naught is the time of the periastron passage, which is when the two stars are the closest, and that is in Julian dates. As is normal with using the solver in Excel, you really want your coefficients to be approximately the same size, okay, at least within a factor of 10. So that's what I do here, and then these are the multipliers out here, and these are the answers out here. Okay, so I have fiddled and diddled until I got something that fitted here. It's kind of like just playing around, you know, you just kind of fiddle with the numbers until things get to what you want. And then when you get reasonably close, then in this cell here, I have the sum of the differences squared. And I also have to use weights for each reading. So we just minimize this, and like magic, all the numbers come out there. If anybody's interested, I could show you the procedure when I get my laptop down. So anyway, if you do these, if you do this fitting, then we see here the quadratic term is negative. So in spite of the fact that if we plot the straight O minus C curve, which looks like the period is increasing, if we actually subtract off the component due to the light time effect, then we find that the period is actually decreasing. So that's kind of cool. So light time effect modeling is a lot of fun. Okay, here's Hill's computing comments that I put in here to try to motivate you folks. We commend those observers who continue to measure times and minima, for it is this wealth of data that makes the parallax determination possible. Now that the period has changed significantly, continued observations are needed since the known orbital light effects, time effects are linked to any short period analysis. So he's trying to convince people to fight the good fight and keep those data coming in. This is one, and I'm absolutely shamelessly tooting my own horn here. I consider myself fortunate to stumble into this. Let's put it this way. Here's a, I keep doing that. Here is a O-C curve for this star, Orionis. What in the world is going on here? I mean, this is quite complex. You know, you've got a dip here, and then almost around there, and up over here, and it's got some wiggles and stuff. These are photographic. The yellow pyramids are visual. You can see the scatter there. The red circles are photoelectric, and the black squares, black diamonds, are CCD. So anyway, this is the fit that the data that we have. Cui himself, back in 1958, noted the period increased very strongly after 1952. I don't have a date on this, I'm afraid. I presume that's the bottom of the first dip there. Geeking, probably not the right pronunciation, back in 1994 proved that there was a third star. Some people suggest that a light time effect, 1982, but there are other explanations. Lame back in 2010. Japanese Journal on Astrophysics and Astronomy drew this plot that noted it does not support periodic behavior, therefore it doesn't support a third body. So this is one of those times when you just jump in and, aha, gotcha. And, you know, I just stumbled on this, I have to say, and my techniques worked, and I was able to get a very nice fit to this. I mean, it really fits nicely. It even goes through all the middle of these inaccurate visual points, and then it fits everything quite nicely indeed. So I somewhat arrogantly, I may come to regret this, titled the paper and updated a definitive solution. So I may end up with egg on my face if subsequent data prove me kind of wrong. So anyway, unfortunately, the problem with new astronomy is, or at least this instance, the referee wasn't very good. There were no corrections. So I thought, aha, got it finally. But I made some real bloopers in there that I didn't pick up. I mixed up I know better, but it's one of those things you don't sort of notice when it's your own paper. Somebody else should read it, actually. I mixed up the eccentric anomaly with the true anomaly. I know the difference, but it wasn't, it didn't get picked up. So anyway, from the data here, one can subtract off the light component, and you get this lovely parabola here. I mean, it really is quite nice. So that works. And then alternatively, in your spreadsheet, if you subtract off the parabolic component, then this is the cyclic component. So you can see that it's not a sine wave. The orbit is eccentric. And so we get that kind of shape. So if all is well, and I've got it right, then subsequent data is going to fall nicely on these curves, and all will be well. Maybe. Here's another one. Again, shamelessly tooting my own horn. TZ booties. This one is really weird. Before I started this game, I didn't know what to do with these. I mean, this was what I called a bouncing ball one. I mean, it sort of looks doink, doink, doink. How could this work? These guys here from the large Asian country with the red flag concluded that there was a long-term period decrease, and then they wanted to talk about jumps in the period. I don't any longer believe in jumps in period. I think the light time effect can fit most of these. Awadallah, I think he's Turkish, got this fit, which, to be fair to him, these points weren't available to him. So this is common in this game. Da, 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 da. So I tried the light fit, and this is with one star, okay, but it doesn't fit all that well. So then I threw in another star and got that fit, which is not too bad. It looks kind of neat. I keep getting points out here, and then I have to solve for the constants again. So, am I getting it right? I don't know. If you look at the residuals from the light time effect, you get, some people are slow learners, you get this curve here, which is, it's a little bit of a parabola, maybe, but if you, I don't like it. Well, first of all, it depends critically on that point there, which we don't like, and also the scatter here is enormous. If you look at the coefficient of correlation, I think it's about 20% or something, so it's not very good. I would not put a lot of credence on that number at all. And I think, when we publish things, we should say this sort of thing. So this is based on what solutions I have, this is the predicted future behavior. So it's going to do some really wild things here. I predict that it's going to go way down here, and this sort of thing. So each big division is 16 years. So I won't be around for this one, or that one, or in here probably. So it's up to you younger guys to keep doing this. So, some interesting things are predicted to happen to this star. And here's another one, AU Serpentis. This is part of my series of period change papers. And I came up with about 3 different solutions for this. I'm not the first in the game. Some other people, it was discovered by Hofmeister. He's a giant in the history of eclipsing binaries. He discovered so many back in the 30s and 40s. And Binnendijk is another giant in the field, obviously from the Netherlands. So other people have been studying this star. Güral, who's from Turkey, performed a light curve analysis and a period analysis. Doggone air conditioning is making things jump around. He thought that there might be magnetic cycles. Okay, this is the joker in the pack. Magnetic cycles can change the size of a star and hence the light that it's emitting and so on. And it's sort of a semi-periodic way. There are ways to test for this. You have to have a number of things going on. Anyway, so this plot here is from Güral. And this is quite problematic because we have some early photographic results here and also over here, and they're quite awful actually. And what do you do about them? These values in here are photoelectric, the first photoelectric ones. We've got some more here and a few there, and then a bunch of CCD ones at the end. So this is one of the models, 29-year large orbit, P3. And Güral got 28.7 years. That's similar. I have 2 other models. And then this is one with a 94-year period for B3. It goes through those photographic points better. You see, this one is kind of troublesome because we don't like humps here where there are basically not many data points. I showed you one earlier, and you really don't want to do this if you can help it. This plot misses these points entirely, which is worrisome. So in this one here, this fit here, the 94-year period one, seems to fit those earlier ones, but it doesn't fit the later data very well. Some things we don't like about this one. We thought we had it nailed. Kevin is publishing a paper. I'm a co-author on this star, and this was what we got recently, a 95-day period. So it goes through the early photographic points reasonably. It sort of fits the other stuff, and it sort of looks okay. And there's some outlier points on the right there, and it doesn't. The last point there is mine. It doesn't fit very well. And then just a couple of days ago, Kevin got a better fit, and what he did was he said, "Okay, let's just chuck out those earlier points. Just ignore them; they're horrible." And so he's come up with a fit that looks like that, which fits a lot nicer. They're the residuals, so it looks like a nice parabola. And this is, it's not quite a sine wave because the eccentricity is about 0.17. So this looks nicer. So this is, to me, that's a lot more believable. And it might be right. It's his paper. Kevin wrote it, and I helped. I asked him to put all the weasel words in, that we use in science. Like it's likely that further data may change this, but this is what we think, kind of thing. You always want to say those things. Here's another one, V1191 SIG. And if you look at the O minus C curve there, what the heck? We have an early observation, and I think that's 65. So it's probably photoelectric, I think. It wasn't just visual. So it looks like a bit of a parabola at the end there, but, so it's probably a light time effect again. What are we talking?
Could it be a cycle count error?
Oh, exactly. That's the whole point. Sorry, my hearing loss is really a problem here. I have to deal with that. Yeah, that's the whole thing. That we don't know what the correct cycle count is for that early one. And so here are 5 possibilities. So what do you do? So I've got 5 different solutions for these. Well, actually, I think it's 6. Yeah, because I've got 3 that go through this one, 2 that go through that one, so it's a whole lot of them. So the bottom right-hand corner is the different fits. They fit the data that we have, but then what's going to happen in the future? I don't know. It gets worse because, so this is 2026, so that's 8 years from now. So maybe in 8 years we can distinguish between, there's difference between the different ones here, but some of them are close, like these 2 are really close, so it's going to be a while. See, it's going to be 2052 before we can separate those 2 guys, so just the way it is. So it's one of the charming things about this game that there are uncertainties and there are lots of things to work with, and so that's what makes it fun. I've saved the best for the last one. This is a really nice one. VWLMI, Leona Minoris, was discovered by the Hipparcos mission only 20 years ago. It's an over-contact binary, 0.478 days. It's a quadruple system. Okay, there are 2 spectroscopic binaries. One eclipses, the other doesn't. Burbula, one of the giants in our field, really, and colleagues were able to unravel all of the spectroscopic data, solving for all the parameters. So there are the answers that they got. So the period of stars 1 and 2 was this, to umpteen figures of accuracy. The time of when they were closest is that. The velocities, amplitudes of their orbits are that. Then he has the masses here. So, they've solved the whole system, but they didn't take the last step. When you look at the O minus C curve, what I did was I took the non-eclipsing pair. I just imagined that they were a single star. And then I was able to use my software to generate this fit. And so I've got a 0.96 year period for the double stars doing this. And it fits very well. But it gets better. This is 23 cycles. And the data it's nailed. This is the most impressive O minus C plot I've ever seen. So the points there's one here, and these guys fit here and there and there and there. They're all right on the curve. So the eccentricity is 0.04, so it's virtually circular. And I think we can say we understand this star system. So Probula, and they did the bulk of the work, and I was fortunate to be able to generate that light curve, which was the first to be plotted. So I put that in period change paper 3, so hooray for me. So closing thoughts about eclipsing binaries. We should now know that times of minimum are important. However, in selecting our program of stars, we need to be smart. We need to select stars that need observing. Okay, I mean, if a star is perfectly regular and lots of other people observe the star, why bother taking more data? Maybe after 10 or 15 years when nobody's observed that star, it might make sense to observe it again, but don't keep doing the same old stars. All of the things we said about good procedures are important, and you need to publish where somebody's going to find it. You can publish in the Journal of the American Association of Variable Star Observers that has have referees, so that's good. My favorite is IBVS, which is the Informational Bulletin on Variable Stars. It's sanctioned by the International Astrophysical Union. It's published online. It's free. You can download the text of each. It's got very good referees. I know I have the bruises to show for it. It's well read. There are no page charges, and they have a very fast publication rate. I mean, they'll get a paper out in a month or two. So, it's a very good journal, and it's underrated. This picture, by the way, is not a sunrise, and it's not a sunset either. So, I'm going to leave you with that. So now, I have some freeware available for all of you. EB minimum is useful for predicting times of minima, stars on your program. Minima is useful for finding the minimum once you have the data. AstroTime is my general program, which does a whole lot of things. There's coordinate conversions, local sidereal time, it's all in there. Local time of dusk is kind of neat, it's in there. And Tomcat is one of them as well. We also have this database. This is where it is on the AAVSO site, if you can find it. If you can't find it, the search up here will find it. I think that's what you should be using. I'm not sure. I'm probably not going to maintain this anymore. I think I want a better site. I don't know where it will be, but whatever. So I have the entire collection on my little, I keep passing this around, which is just fine. So if anybody wants to copy to their laptop, feel free. There are 8,000 files, so that's good. If there's time, I still have an audience, so we can talk about some other things.